thank you very much. I want to thank the organizers for the opportunity to present my research here, which is on centrifugal microfluidics and how it can enable high dynamic range PCR in 4 picoliter microwells. And well, the challenge that we are addressing, like I guess many others of you, is finding rare cell-free DNA or circulating tumor DNA. And yeah, like publications have shown, these can be very rare, down to like 5.5 parts per million or 0.003%. And like other publications have reported. And obviously, how to detect them, we need some very nice digital PCR with very low limit of detection here. And well, looking at a little bit of the theory, like how is the limit of detection defined? It's usually defined as a function of the partition number. And this is just some simulated data or simulations on how this scales actually. So there's a linear correlation. And so you this is like the data for like 2,500, 25,000 or 250,000 partitions, how it scales. And further, you can also, by increasing the partition number, the partitioning error decreases a lot. And by decreasing the partitioning error, you can also extend the dynamic range massively. And this is also what we set out to do. And so, looking at the state of the art in well-based commercial partitioning systems, dPCR systems, well, I mean, there are like several devices already there, which are great in general. And yeah, but as you can see, like they vary between like 20 to 100,000 partitions per sample typically. And this is basically the limit where it's currently at. And what limits actually the partition number? So the partition number is usually limited by the space or by the area that you give for the partitions. And typically you have like partitions in the nanoliter scale. And so you have a certain amount that you can fit into one chip that fits into this device you want to process the chip later on. And so to increase the partition number, we have to shrink or to downscale the partition size actually. And yeah, so partition downscaling, however, comes at some other issues, especially at fabrication, at partitioning itself, how you partition the fluid inside these small partitions, and evaporation control. And yeah, I'd like to present you now our solution or our research on how we use centrifugal microfluidics. And this is a centrifugal microfluidic LabDisk that you can see here, with a partition number of over 250,000 microwells per sample, with a scalable fabrication process for our LabDisk. Using the centrifugal microfluidics, we can have a very fast and homogeneous partitioning of our liquids or of the PCR reaction mixes. It's suitable for different kinds of liquids or for different PCR reaction mixes. It's not dependent on a single one. And also, again, using centrifugal microfluidics, we can also effectively avoid evaporation here of these very small volumes. So first of all, to just give you some insights on how this LabDisk looks like basically, or how it's fabricated. So we want to have some microfluidic chambers and channels here. And for them, we do some micromilling here. So we micromill into PMMA. And that structure, this microfluidic layout, we cast into PDMS. And then we use microthermoforming to replicate the structure or the layout into a thin foil of COC polymer film. It's like 500 micrometer thick. And then we have another side where we have a lithography process to produce these microwell structure into silicon or nickel using lithography. And this master tool has like a well density of 115,000 microwells per centimeter squared and a microwell volume of 3.7 picoliters. And so again, we use PDMS to replicate the structure. Again, we use then hot embossing to get this microstructuring into another thin foil of COC. So we have these two foils of COC, and then what we do, we use thermal bonding to actually bond these two COC films onto each other. And by that, we get these LabDisks that I showed before. And yeah, as you can see, although we use thermal bonding here, we can get the replication process, and we can preserve the picoliter features here without melting of them, which is of course critical. And next, I'd like to show you how the fluidics work now. So this is a LabDisk, and we have this overflow inlet microwell array and waste chamber here. And one of these array contains 260,000 microwells, and as we have 12 of these inlets on one disk, it's like over 3 million microwells per LabDisk. And so what we do, at first, we pipette the reaction mix, the PCR reaction mix, into the inlet. We then use centrifugation to actually let the liquid flow through the channel into the microwell array chamber, fill it up to the top. And you can see it in the side view, all the microwells in the bottom foil get filled by that. And then, because we have a siphon connected to the side of the microwell array chamber, as soon as it reaches the top, all the liquid gets drawn out again. And the crucial part here, however, that our microwells are so small that the capillary forces in there keep the liquid inside. So the liquid does not get out again, and it remains inside these microwells. And that enables us to then stop the disk. We pipette some oil on top. We rotate it again, and so the oil comes, flushes across everything, and finalizes basically the separation of the microwells, and also is there, of course, to prevent evaporation. And the nice thing here is using centrifugal microfluidics is that it can actually allows us to prevent some capillary filling of this whole chip and everything. We can have it in a very controlled manner, which I will show you now how it looks like. I have a video prepared. I hope it plays. Let's see. Yeah, so this is now actually how it looks under rotation. There's a reaction mix coming, filling up to the top, then gets removed again, and then we stop the disk, we pipette some oil on top, and comes and flushes across everything. On the right side, you can see zoom in how it looks then. This is like the partitioned PCR reaction mix with some background dye in there. And so like this, we can actually partition, using all 12 inlets, we can partition liquids in over 3 million microwells within 2 minutes, so it's also very fast. Next, I'd like to talk about the robustness that we get here. So these are 3 different PCR reaction mixes. And as you can see, they have quite varying contact angles, like between 57 to 73 degrees. So these are like the wetting properties on how they, on the wettability on our COC polymer. And also they have quite different dynamic viscosities, ranging from 1 to 8 millipascal seconds, with 8 already being quite high. And obviously, I mean, of course, you can see that the partitioning looks different from one mix to another. But the crucial part for us is here that it's uniform. It remains uniform. Doesn't matter which reaction mix we use from these that we tested. This is crucial for us to perform the PCRs. And yeah. Next, I'd like to talk about the thermostability now. So this was also very critical for us to solve because, obviously we have these very small volumes of 3.7 picoliters. And this is how it looks like our chip when we use no rotation, when we just have it standing and we heat it up. So there's like air dissolved in the oil, and when we heat it up, the gas solubility of our oil decreases, and therefore these air bubbles emerge there. And since, as you can see, like that or if we don't have oil on top of our microwells and we heat it up during thermocycling, these reaction mix partitions, or the liquid inside evaporates into these air bubbles. And again, what do? We use centrifugation, because that can actually effectively remove all the air bubbles from inside this array chamber. And by this, we can actually, keep the partitions, or keep the partition volume, and keep especially the evaporation barrier that the oil builds. We can keep it intact. And now I'd like to show you our proof of principle. So this is like a KRAS G13D assay, like short fragmented, like how it's commonly found also in liquid biopsy, but it's G-blocks so far. And as you can see, this is like how it usually looks like, with a low, medium, high concentration. And what we've done so far, we are at the start of investigating this now, is to quantify. We have a reference device with the QIAcuity that we compared to. And so far, I mean, we get an excellent linearity so far with our quantification. It's 6 replicates. And so far we can show that we get this very good linearity, and that we are so far thinking that we can actually have an absolute quantification with that. But this also brings me to our outlook. What are our next steps that are missing so far? So first, I mean, we still need to verify the microfluidic and quantification robustness of our system. I'm currently still in the process of improving our imaging and image analysis pipeline, actually. And then what is still missing, we have to demonstrate this, that our extended or increased number of partitions really extends the dynamic range, and that it also improves our limit of detection. And with that, I'd like to thank our my colleagues, our collaborators and funding partners, of course, that make all this possible. And yeah, thank you for everyone for your attention, and I'm open for your questions.